Hi, in this video we are going to talk about topological ordering or topological sort and its applications. So let's get started. What is topological ordering? Topological ordering of a directed graph is a linear ordering of its vertices such that for every directed edge from U to V, U comes before V in the ordering. It's very important that the graph has to be directed. For an undirected graph, basically there is no point in defining a topological order because every order is a topological order. Okay, so it's very important then when we have directions, when we have some constraint. For example, we are not able to go from vertex A to vertex B. These are the situations when topological sort came to be. So for instance, the vertices of the graph may represent tasks to be performed, and the edges may represent constraints that one task must be performed before another. And basically that's why I said that there is no point defining the topological order for an undirected graph, because we define these constraints that, for example, one task must be performed before another with the help of directed edges. So in this application, a topological order is just a valid sequence for the tasks. It's very important that we can use topological ordering only if the graph has no directed cycles. That's what we call a DAG, directed acyclic graph. So a graph that doesn't have any directed cycles. Okay, so any DAG has at least one topological order. Okay. It's very important that topological sort has a linear time complexity, and it is important in project management. Another important fact has something to do with Hamiltonian cycles. What is a Hamiltonian path? It is a path in an undirected or directed graph that visits each vertex exactly once. The Hamiltonian cycle is a Hamiltonian path where the starting vertex is the same as the vertex where we finish, or Hamiltonian path. So basically it is a closed Hamiltonian path, and hence the name Hamiltonian cycle. It's very important that finding the Hamiltonian cycle is an MP hard problem. It's very hard to construct any algorithm that's going to find the Hamiltonian cycle. But if a Hamiltonian path exists, then the topological sort order is unique. It means that we have a single topological sort order. It's very important that sometimes for a given graph there may be several topological orders, but for Hamiltonian path the topological sort order is unique. We have a single topological sort order, so no other order respects the edges of the path. Conversely, if a topological sort doesn't form a Hamiltonian path, then the directed acyclic graph will have two or more valid topological orderings. So it's very important that finding the Hamiltonian path is an NP-complete problem, but we can decide whether such a path exists in linear time. Why linear time? Because constructing the topological sort has linear time complexity. Just to be clear, we are not able to find the Hamiltonian path in linear time complexity, because if we could do so, then this problem wouldn't be NP-complete, because we could construct a linear time complexity algorithm. But finding the Hamiltonian path is a very complex problem, but we can decide whether such a path exists in linear time. Okay, if you come to the conclusion that there is a Hamiltonian path, then we have to find it. But maybe we don't have to search for a Hamiltonian path if it doesn't exist at all. Okay, so let's see a concrete illustration. We have 5 vertices A, B, C, D, and E, and directed edges represents the constraint. What does it mean that, for example, the A has an edge pointing to the vertex C? Then in order to do the vertex C, in order to do this step, for example, in project management, then we have to do vertex A at first. And basically, the algorithm is that we have to find a vertex with no incoming edges and keep repeating it over and over again. So the first one is, for example, A. The A doesn't have any incoming edges. So it's going to be the first in the topological order, and it's very important that we don't want to consider this vertex and its edges anymore. So, for example, we set it to visited with a Boolean flag, and then we don't have to consider it. So in this situation, the vertex C doesn't have an incoming edge because we have already considered the edge coming from vertex A. So the next one is the vertex C. The C has outcoming edges without any incoming edge. Okay, so it's going to be the second one in the topological order. Then the E. The E doesn't have any incoming edges, so it's going to be the third one in the topological order. Then the B. Okay, then the D. So what does it mean? That if, for example, these vertices represent tasks, for example, in software engineering, we have to make the tests, we have to configure the continuous integration server, then we have to find an optimal algorithm, then we have to deploy your application, and so on. We could construct a graph-like structure and we could use the topological ordering. And why is it good? Because it's going to tell us the order in which we have to take the steps, we have to make the issues, we have to solve the problems in order to be able to complete the tasks as a whole. So the topological order will be A, C, E, B, and D. What are the applications? For example, dependency management in software engineering with Maven, Ant, or Gradle. And for example, at universities, constructing the syllabus or the curriculum. Let's suppose the fact that we have 5 subjects we have to complete: Fourier series, calculus, linear algebra, differential equations, stochastic processes. Of course, there are some constraints. We are not able to complete the stochastic processes unless we complete calculus and differential equations at first. We are not able to complete, for example, linear algebra because we have to complete calculus at first. We are not able to complete calculus unless we take the Fourier series. So what will be the topological order? In this case, the Fourier series, calculus, linear algebra, differential equations, stochastic processes. What does it mean? It means that we have to take these courses in this order if we want to complete them, because we are not able to complete linear algebra without completing Fourier series and calculus, because we are not able to take this course. These are the constraints. And as far as I am concerned, the most apparent application of topological sort is Maven, so project management frameworks. Let's suppose the fact that we have an application with several Maven modules. I'm not sure whether you are familiar with Maven, it doesn't matter, it is just the theory. So usually a software builds up of distinct Maven modules. Okay, it can be Gradle modules, whatever. What's important that we have a distinct package, a distinct unit, a distinct Maven module for the UI, for example, for the model, for the service that's going to communicate between the UI and the model. We have some utils storing some constants and some application-specific information. We can have a web service, for example, that's going to make some calculations or whatsoever. We can have a distinct module that's going to communicate with high-performance cluster in order to be able to run simulations faster or whatsoever. What's important then, we have several distinct modules. And of course, for example, the service is going to store the model as a reference. This is why the pom.xml came to be. In the pom.xml, I have the model as a dependency. What does it mean? That I'm not able to build this service unless I build the model first, because the service module relies heavily on the model. And this is the same for the UI. In the UI, I have the util, the model, and the service as a dependency. So Maven has to find out an order in which it's going to build its modules in order to end up with a situation when all the dependencies are satisfied. And basically, this is one of the reasons why Maven came to be. We can use Maven commands in the command line. Okay, you don't have to know anything about Maven, it's just for demonstration purposes. I'm going to hit Maven clean install. Okay, and as you can see, the so-called Maven reactor is going to determine the order in which these modules has to be compiled and has to be installed to the local repository in order to allow other modules to use them as dependencies. And basically, if we come here, then the reactor build order is going to be the manager, then the model, then the service, then the util, and the UI. And basically it is quite intuitive because the UI is going to depend on the util, the service, the model. So this is the order in which the build has to be done. And basically this is why the Maven reactor came to be. It's going to make the topological order in order to decide that what will be the order of compilation. So I think it is a very, very good application for topological ordering and topological sort. Thanks for watching.